Dear students, Assalamu alaikum warahmatullahi wabarakatuh. How are you all? Our today's lecture is lecture number 4, which is about multithreading and multiplexing. Our next lecture will be about broadcast application concepts. So let's have some introduction about multithreading. So we all know that in today's world, multiple users are connecting to the applications. So it's multi-user applications. So while designing the application programs to be deployed on a network, we should keep in mind that we will be receiving multiple user requests simultaneously. So in other words, the application programmers should design the application to be deployed in a network, and they should keep in mind that these applications will have multiple requests. So to meet these requirements in today's modern programming languages and operating systems, these operating systems and the languages are designed to support the development of applications that contain multiple activities, and then thus this can be executed concurrently. So in this lecture, we will focus on learning how to write an application that contains multiple tasks, and then it can be executed concurrently. So in Java, how does it realize this? It realizes this by using multi-threading techniques. So the multi-thread, how it works, multi-threaded. They said here that traditional Java solution for allowing the CPU to race ahead of the network is a combination of buffering and multithreading. In other words, it says, in order to make the CPU race ahead of the network, how do we do that? We achieve that with the combination of buffering and multithreading. So multiple threads can generate data for several different connections at once. And what happens? And store that data in buffers until the network is actually ready to send it. This approach works well for simple server and clients without extreme performance needs. So this point is very important here. It says that the application we will be developing this application will be working by how that they will be storing the data in buffers, and until the network will read or send the data. And they said to achieve this goal, this approach, to achieve this goal, we don't need the servers and the clients to be high performance. Any very expensive servers, very expensive machines, we don't need those things. So this can be this approach can be achieved with very simple server and clients. So the overhead of swapping multiple threads and switching between them can be non-trivial. So let's look into the details and we'll understand better. Now the question is, why to use threads in network programming? The base purpose, the sole purpose of using to use threads in network programming is that as we discussed in the beginning of the lectures in slide 1 introduction, that we are expecting multiple clients to connect to a server simultaneously at the same time. So when we say that we don't want a single client to connect to the server, instead we want multiple clients to connect to the server simultaneously. So we want our architecture to support multiple clients at the same time simultaneously. We must use threads on the server side, so that whenever a client request comes, a separate thread can be assigned for handling each request. If you remember, students, in lecture of TCP, yeah, in TCP sockets, elementary TCP sockets, in that lecture, at the end of the lecture, we discussed about that, what do you call that, fork, yeah, parent and child operation by fork, using for functions. So this idea is similar to that one when it says that whenever a client request comes, a separate thread can be assigned for handling each of that request. Yani a child will be created, a child program, a child socket will be created to handle a new request from the client. So to handle, another point is that to handle priorities in Java, thread priorities, we have an API known as thread.setPriority. So it says that it is important in Java to have to control threads by setting priorities. Priority means that which thread should have more weightage, yani which thread should run first, the other thread's instances will run later, or which thread will be visible and other threads could be hidden at the background. So in Java, all the threads, basically instances, all these instances or threads the developer created have the same priority. So when all the threads, all the instances have the same priority, how can we control them? So for that, as I mentioned before, we will be using threads priority controlled by Java API. We'll be using an API known as thread.setPriority. It is important for different threads to have different priorities. So how do we achieve that? It says important threads should always have higher priority than less important ones, while threads that need to run quietly as a daemon may only need the lowest priority. As a daemon means those threads which have the lowest priority, which will run quietly at the back end, they should be set into lowest priority. So let's see how many priorities we have and what constant values will be assigned in the API in order to set the priorities for these threads or instances. It says the thread class provides three constant values. What are the values? 1, 5 and 10. So in order if we want a thread or instance to run quietly at the background, we will set the thread priority as 1. So when this constant value 1 is set, this will keep the priority of the thread as minimum priority. And if we set the value as 5 in the set priority, it will automatically set the value, the weightage or the priority of the thread as normal, middle. And if we set this constant value as 10, this will be setting the priority of our thread or instance running as maximum priority, the highest priority. Highest priority, lowest priority and middle priority. So these are three constant values. So now let's look at some input-output multiplexing, how this will be achieved in our Java. It says that what is I/O multiplexing? It says the capacity to tell the kernel that we want to be notified if one or more I/O conditions are ready. What do we mean by we? Here we means the application wants to be notified, wants to be informed by the kernel if some datagram arrives at the kernel. If some datagram from the network arrives at the kernel side, so the application wants the kernel to inform that some I/O conditions are ready. One or more I/O conditions are ready. So I/O multiplexing can be provided by select and poll functions. So again I will tell you in very simple words that V means the application. So the application want to be notified by the kernel when one or more descriptors are ready, I/O conditions are ready. And how do we achieve that? We will be using some select and poll functions. So what are the scenarios or what are the applications for I/O multiplexing? If you read these 5 scenarios, examples, applications that are used for I/O multiplexing. So this is in the first case it says a client handles multiple sockets. This is quite rare, which is happening in TCP client, in TCP client size. So the other one says client handling multiple sockets. This is also happening, but another example of this, the example for this one could be as a web client, not TCP echo client, but web client. Another application for I/O multiplexing could be for the server, when the server handles both listening socket and its connected socket. This is happening in TCP client server on the server side when the server is ready for listening, and at the same time the server is connected as well and is expecting another client to be connecting to the server. So when the server is in both states, it's ready to connect another one and is already connected with the previous one client. So in this scenario also we say that I/O multiplexing is implemented, applied. The fourth scenario could be a server handles both TCP and UDP sockets. A server handles multiple services and protocols. So all these could be applications for I/O multiplexing. Now our next topic is the I/O models. What I/O models could be used to achieve or to apply the I/O multiplexing? They said we have 5 I/O models. So what is the purpose? And we're looking into it, how it works. It says these I/O models, there are 2 distinct phases for input operations. What are those distinct phases? One could be waiting for the data to be ready, and the other could be copying the data from the kernel process to the application, or from the kernel to the application process. So we will be looking into it, that what do we mean by waiting for the data to be ready. So when we say that waiting for the data to be ready, it exactly means that the application is waiting the data to arrive at the kernel. As we mentioned before, when the data arrives at the kernel side, the kernel will notify the application. So here they are saying that waiting for the data to be ready, and the second phase will be the application will send a system call that will go and copy the data that arrives at the kernel, and it will come back to the application. So what are the 5 I/O models here we'll be discussing are blocking I/O, non-blocking I/O, I/O multiplexing that will be using select and poll function. Then we have signal-driven I/O. Here signal-driven I/O will be installing signal handler by using SIG-IO. And then the last one is asynchronous I/O model. So let's look into it one by one. The first one is the most common I/O model, and it is known as blocking I/O. So why is it the most common, and what do we mean by blocking I/O? Let's look into it. The process in the application side calls the system call receive from. It sends a receive from. It calls receive from, and the system call does not return until the datagram arrives, and this is for default, and this is default for sockets. Now, what does this point means? Let's look into the diagram. Here, if you look into the left side, we said this is the application side, and on the right side we said this is the kernel. So what happens, the application program, it wants the data to be copied from the kernel and come back up to the application side. So for this purpose, to copy the datagram, the data back to the application, we are using blocking I/O model. There are different I/O models, as I mentioned before. We'll be using 5 I/O models. So each model has some features in it, some properties. We'll be discussing it. We'll be explaining the diagram. We'll see how the diagram, in the diagram, how it works exactly. So the purpose is again what? That we want the application to send some system call and copy the datagram from the kernel and back it to the application. As I said, the process calls receive from. The process calls receive from system call. This is sent to the kernel. But when it reaches the kernel side, it says, oh, the datagram is not ready. No datagram ready. There is nothing to copy. So what happens? We keep on waiting for the data. So how long do we wait? We wait until the datagram is ready. It says, during that, the process is put to sleep if blocked. So it says, we wait till the datagram is ready. And what is happening? Process blocks in a call to receive from. So from here till this stage, the process is in the wait stage. Why? The system call went to the kernel to see if the datagram is ready. The datagram wasn't ready, so it was waiting, and it kept on waiting until the datagram arrived. It's still there. It copies the data from the kernel to the user side. When the copy is complete, so from here to this stage, from here to this time, the process is put to sleep, block mode. And then the datagram was copied, successfully returned, okay, process completed. So it started from here, received from, until the process arrived with the datagram. So why is it called blocking I/O model? The reason being that from waiting the data till copying the data, the process was put to sleep block mode. Okay, let's look into the next I/O model, which is known as non-blocking I/O model. So what is happening here in non-blocking I/O model? It says when an I/O cannot be completed, the process is not put to sleep. Okay, when an I/O cannot be completed, the process is not put to sleep, but returns with an error. And what is the error? What is the notification? It's error would block. Let's look into the diagram. It says the application calls system call receive from. And this receive from goes to the kernel side and looks for some data, if the data has arrived. So when it reaches there, it says no datagram ready. So it instead of waiting like it wait in the blocking I/O model, wait for the data. In this situation, it says we are not going to wait. Instead we just come back with a notification with error would block. So the next time again the application call receive from system call, again it goes there and found that the datagram wasn't ready. It comes back with would block. So this thing happened multiple times, several times, until this receive from system call was sent and the datagram was ready. It copied the datagram and then it returned with OK, and the process was completed. So here you can see the difference with blocking I/O, that the system was not put to sleep. The system was not put to sleep. So all this time, starting from here till here, the system was not put to sleep. The system was put to sleep or block only for the time of copying the datagram from the kernel. So in this time also only the system was put to block mode. Otherwise it was non-blocking I/O. Process repeatedly calls receive from. Process repeatedly calls receive from. Process repeatedly calls receive from, waiting for an OK return, polling. Waiting for an OK return known as polling. So this was polling and this was non-blocking I/O, and this would be considered as waste of CPU time. When is it considered as waste of CPU time? If this model is not used properly. If we use this model properly, we will not be considering it as waste of the CPU time or waste of the resources. Otherwise, we'll say that non-blocking I/O model is waste of resources, waste of CPU time. Here we set the socket to be non-blocking. Okay, we set the socket to be non-blocking for some time. It's non-blocking. That is why it's called non-blocking I/O. And what we are doing, we are periodically, frequently, we are checking, polling that the datagram arrived or not, the datagram arrived or not, until it arrived. So these few points we need to keep in mind, that waste of CPU time, which is very important point. And we are setting the socket to be non-blocking. And we are looking for the datagram, whether it has arrived or not, periodically means frequently, using polling method. Now let's look into the next I/O model, which is known as I/O multiplexing. What is happening here in I/O multiplexing, they said we'll be using select or poll to report if some descriptor or variable is readable or writable. Let's look into the diagram and understand. So it says we'll be using, instead of one system call receive from, as we have been using previously, receive from system call in blocking and non-blocking I/O models. Here we'll be using two system calls instead of one. And what is the system call? The other one is select. And we will be using select or poll. So it says here the select system call is called, and what happens here, the process blocks. The process is put into process blocks in a call to select, waiting for one of the possibly many sockets to become readable. So when this is called, when there is no datagram ready on the kernel side, so the process is put into sleep or block mode in waiting for the data to be ready. When the datagram is ready, this comes back with readable and says return readable. It didn't copy. It just said come and inform the application that the datagram is readable. So this is what we said. It says it will be reporting if some descriptor variable is readable or writable. So it is informing, it is telling the application that the data is readable. So when this point comes here that the datagram has arrived, so receive from call, system call is sent. This is the second system call received from, which is sent by the application, is called by the application. And this system call goes to the kernel side to copy the datagram, and then it copies the datagram, and the copy is complete and return OK, and the process is complete. So here also what happens, the process blocks while data copied into the application buffer. So we need to keep in mind that while calling two system calls instead of one, we'll be putting the process into block two times. Process blocks in call to select, process blocks while datagram copied. So that is why we call it IO multiplexing model. So then it says here, what does it say? At first, this does not appear to be an advantage over blocking IO. In fact, why we are using two system calls instead of one? This is also what you call waste of resource. We are using resources. But then it says the advantage is that the select can wait on more than one descriptor to be ready. So this is good. This is an advantage that the select system call, it can wait for one or more descriptors to be ready. So when one or more descriptors are ready, it comes back and inform one time. Then this receive from system call is called, and it will go and copy all the datagrams that arrived. So instead of calling one and go and copy one datagram, so it says it does what? Select can wait on more than one descriptor to be ready. So this could be an advantage in IO multiplexing, IO model. Let's look at the next one. The next IO model is signal driven IO model. And what happens in this case, in this model, they said we first enable the socket for the signal driver, input output. And then, and how do we do that? It said in order to enable the socket for signal driver, it says we install signal handler. How do we install signal handler? We use sig action system call. So in other words, sig action system call is used by the application to install signal handler at the kernel side to enable signal driver. Sig action system call is used by the application process to install signal handler to enable signal driver on the kernel. And it says the return from the system call is immediate and the process continues. Let's look at the diagram and we understand better. In the diagram it says we establish sig IO by calling sig action system call. So this sig action system call goes to the kernel side, installs signal handler and returns immediately. And during this time, it says the process continues executing. It's not put into block state. On the other side, waiting for the data. The kernel is waiting for the data. The signal handler, the sig IO, is waiting for the data to arrive. So as soon as the datagram is ready, what happens? A signal is delivered to the application, to the signal handler. A signal is delivered. What signal? Input-output signal is delivered. What is the purpose of this signal? This notification is to inform the application, the signal handler, that some datagram has arrived on the kernel side and please send some system call receive from to go and copy the datagram. Let's look into it. It says when the datagram is ready to be read, when the datagram is ready to be read, the sig IO, the signal input output signal is notification is generated for our process. For our process means for the application. So what will the application do? Definitely it will be calling receive from. We can read the datagram from the signal handler by calling receive from, which goes to the kernel side and which goes to the kernel side to copy the datagram. So the advantage is that the process is not blocked. Definitely, how will the process be blocked? When the system, when the sig action has installed signal handler. and there is no system call waiting. There is no there is nothing waiting for there to wait for the data to be ready, datagram to be ready. So that is why we say that what is happening. The advantage is that the process is not blocked while waiting for the datagram to arrive. So this is very interesting. We install signal handler. A SIG-IO is delivered to the signal handler. Receive from system call is sent to copy the datagram, and the datagram arrives. The what we call the process system call returns with OK. So process continue executing. The process is blocked only while copying the datagram into the application buffer. So only this time, this duration from here to here till here, the process is put to what you call block state, which is very short time. Okay, let's look into the next IO model, which is asynchronous IO model. Here it says this is quite simple actually and very interesting how it works. It says these functions work by telling the kernel to start the operation and to notify us means the application, when the entire operation is complete. So very interesting. Asynchronous input output read. System call is used and then it returns immediately. So what is this doing? This is telling the kernel that we are using asynchronous input output. What happens? The main difference between this model and the signal-driven I/O is that with signal-driven I/O, the kernel tells us when an I/O operation can be initiated. So in signal-driven, what was there? That the kernel is telling us when the input-output operation can be started. While in this one, with asynchronous, the kernel tells us when the operation is complete. Yani, let's repeat the point again. In signal-driven I/O, the kernel is telling the application that it's time to start the operation, and it's time to read, it's time to copy the datagram from the kernel to the application. But in this situation, instead of informing the application, the kernel tells when the whole operation is complete. So this is kind of automatic asynchronous. What is happening? Asynchronous I/O read system call is used to inform the kernel that we are going to use asynchronous input output. So what happens? When the datagram arrives, it's being copied the datagram from kernel to the user. The copy is completed and it delivers the signal specifying that it was an asynchronous input output read. And the signal handler, it processes the datagram. So process continue executing from start till the end, from the beginning till the end. So this one again, in simple words, asynchronous the kernel will inform the application. The kernel informs the application only when whole the process is completed. This is quite simple, and so we need to keep in mind that what are the differences in these models, IO models. So if we look at the blocking IO model, what is the difference between the first phase and the second phase? Similarly, the first phase and the second phase. So let's keep in mind the two phases, the two phases, waiting for the data to be ready and then copying the data from the kernel to the process. So these two distinct phases for the all 5 IO models, we'll be looking into the summary. Okay, the summary says that we are going to compare the comparison of IO models. Now here we need to look into it very deeply. So this is our blocking IO model, non-blocking, IO multiplexing, signal driven, and asynchronous. So it says we already know that we have two distinct phases for all IO models. The first phase was waiting for the data to arrive for all of them, waiting for the data to arrive, and the other phase was to copy the data from the kernel to the user side. On the other hand, if we see this, it says what is happening. The first phase, yeah, in the first, second, third, and fourth IO models, in the blocking, non-blocking, IO multiplexing, and signal-driven. In these four IO models, the first phase handled was handled differently. Yeah, the first phase in all of them was handled differently. Second phase was handled the same way. So in the second phase, four of them were blocked. So blocked in a call to receive from was blocked in a call to receive from. Whereas in the fifth one, the asynchronous, in which we said that AIO read was used, in this IO model, both phases handles both phases the same way. So it was, as it was asynchronous, it says it was initiated and notification was sent, AIO read was sent, and the application was informed when the entire operation was complete. So after this, we need to see how our select and poll functions worked with us. So let's look into it. It says the select, what did it do? It allows the process to instruct the kernel. It allows the application process to tell the kernel, to instruct the kernel to wait for any one of the multiple events to occur. Yeah. And to wake up the process only when one or more of these events occur. So we are using and, or for this select. Means what? That this select is used, is working in this and this scenario, or this scenario. So it also works to wake up for the process only when one or more of these events occur, or when a specified amount of time has passed. It's now explaining to us this and or. For example, we can tell the kernel to return when descriptor is readable, when the datagram is readable, it's ready to be read. The other option it could be, and descriptor is ready for writing, or a descriptor has exception condition pending, or specified time has expired. Meaning some amount of time has passed, so now you need to come back to the application process. So select is used in this scenario, or this scenario, and this scenario, or this scenario. So these are the four ways where we say that our select was used, select call. So what are the timers for select? It says select three ways for the timeout. So the select could wait forever on the kernel side. What does it mean? It will return only when one of the specified descriptor is ready, and when the datagram has arrived. If the datagram did not arrive, it will have to wait at the kernel side forever. The select system call, wait forever. The other one says wait up to a fixed amount of time. So if we look into it, where did it wait for fixed amount of time? It was somewhere here. So it says wait for some fixed amount of time. Select system call. So wait for some fixed amount of time. So when the datagram was ready, it returned readable. So this was the some fixed amount of time that it waited for it. And in the other scenario it says, don't wait at all. Return immediately after checking the descriptors. So it also happened in one of the IO model that it did not wait at all. It went and checked. If there is nothing ready, it returned immediately. So these are 3 timers for select. Another thing we need to keep in mind is the conditions for the socket readable. When are we going to read from the socket? So we have 4 cases, 4 conditions. It says the socket will be readable if the number of bytes in the receive buffer, the number of bytes in the receive buffer is greater than and equal to the current size of the low water mark for the socket receive buffer. It means if some minimum amount of data is present, so greater than or equal to the low water mark. So if something is there at the low water mark, there are some watermarks. Watermark means some level that we have set in the buffer. If the data is less than that level, we say that it's low, is less than the low watermark. But when will the socket be readable? In our case, it says if the buffer size is greater than, the data is greater than or equal to in the buffer, the low water mark in the socket receive buffer. So then what will happen? This is called condition for socket readable. So we said that the read operation will not block and return greater than 0 bytes. So definitely if the data in the buffer is less than, not greater than, is less than the low water mark, so the read operation will not work. It will be blocked. So when will it not be blocked? And it will return with some bytes, not 0, when the receive buffer is greater than and equal to the current size of the low water mark. What is the other condition? The second condition for socket readable, it says here the read half of the connection is closed. So we all know that in TCP client server, the clients connect to the server, and a 3-way handshake is being done, and then some read write operation is being done, and at the end the client calls close. So when the TCP has received a finish synchronization bit, so when the read half of the connection is closed, it says read operation will not block and will return 0. This is another scenario. So we are looking at some conditions for the socket is readable, when the socket is readable. It says in this situation also the socket is readable. In this situation, TCP client server application, the socket is readable even when the read half of the connection is closed. But there is something to be read. So it says read operation will not block and will return 0. The third condition for the socket to be readable is the listening socket and completed connection queue is empty. So when a server is listening for the client to connect, that is the time we call it listening socket. And completed connection queue is empty. It says here accept will normally not block. And the fourth condition for socket readable is socket error is pending. Here it says read will not block and return with error -1 and error number set to specific error condition. So this is another one. Socket error is when some error is pending in the socket. In that situation also socket is readable. Unless until the error is removed, the socket is readable. When the error is removed, then the socket is no more readable, the connection is closed. So similar situation is there when there are some conditions for socket writable also. So what are the conditions? They are quite similar to the conditions for socket readable. As in the readable says the number of bytes in the receive buffer is greater than or equal to the current size of the low watermark. Similarly, in the socket is writable when the number of bytes in the send buffer, in this case receive buffer, in this case send buffer. So the number of bytes in the send buffer is greater than or equal to the current size of the low watermark for the socket buffer. So if the socket is set non-blocking, we have two scenarios. If the socket is set non-blocking, write operation will not block and return greater than 0 bytes. So this is for sending, and that one was readable was for receiving. The other condition is write half. In this case was read half. So here it says read half of the connection is closed. In the TCP client server, here it says the write half of the connection is closed. That is, TCP has received a finish synchronization bit. Write operation will generate sig byte. So in this case also the socket is writable. And you can keep on sending your data. You keep on sending your data into the buffer. Even when the TCP has received a finish synchronization bit. The third condition, it says socket error is pending. Write will not block and return with error -1 and error number set to specific error condition. It says unless the error, socket error, has been removed, till then you can write, you can send, you can write. The socket is writable. So at the end, this is some summary of the conditions for readable, writable, exceptions. Yeah, what is the exception for? TCP out of band data. And then we have in readable and writable both, it says pending error as mentioned before. Socket error is pending. In readable also, socket error is pending. In both cases, it says socket error pending. It's there. So we already discussed the conditions. Data to be read, read how the connection is closed. Space available for writing, write how the connection is closed. So readable, writable, error pending, and then TCP out of band. So students, this was our lecture number 4, and if you have any questions, definitely you will have to ask your course instructor in your respective colleges. That is Sohar and Sur. Every students will ask his teacher, their teacher instructor in every, and of course we are there to help you all. Thank you very much for attending this lecture. Kindly revise the lecture, read the lecture, understand the lecture carefully, and prepare yourself for the assessment. Thank you very much. Have a nice time. Goodbye.